In this chapter, we're going to explore a really critical topic, testing non-functional requirements, or NFRs for short. We're going to move beyond just making sure an application's features work and dive into how we make sure that software is strong enough, scalable enough, and secure enough to actually survive out there in the real world. I mean, we've all been there, right? You're trying to snag a deal during a huge online sale, and bam, the site crashes. Or you're using your favorite app, and it just grinds to a halt. Well, that frustration is usually a sign that a project didn't pay enough attention to its non-functional requirements. You see, functional requirements tell us what a system should do, but NFRs tell us how well it should do it. Things like performance, security, reliability, and when they get ignored, well, you definitely feel it.
So, first things first, let's get our terms straight. People tend to use these words interchangeably, but in engineering, they mean very different things. Performance is all about speed for a single action. How long does one thing take? Throughput is about quantity over time. How many of those things can we get done in an hour? And capacity kind of brings them together. It's the maximum throughput you can handle before your performance starts to stink.
And I really can't overstate how important this is. Putting off testing for these kinds of requirements is just asking for trouble. It creates a huge amount of project risk. I mean, imagine finding a massive security hole or realizing your app can't handle more than 100 users right before you're supposed to launch. It can lead to total disaster, major rewrites, blown budgets, and sometimes it can kill the project entirely. So, how do we get a handle on this risk? Well, it all starts with being super clear and specific. We have to go from vague wishes like the system should be fast to solid, measurable, and testable goals. This first step is all about defining exactly what good enough really means for us. Now, you might see a statement like this and think, hey, that's specific, it has a number. But honestly, on its own, this is dangerously vague. It's missing all the context that would make it a truly useful or even testable requirement. To make that last statement mean something, we have to start asking some clarifying questions. For instance, 80,000 transactions per hour. Under what conditions? Is that during an average Tuesday, or is that during our Black Friday peak? And what happens if one of our servers goes down? By asking these kinds of questions, we start to turn that fuzzy goal into a set of very specific, very testable scenarios. This brings us to a classic phrase you hear all the time: make it as fast as possible. Let's be clear. That is not a requirement. It's a wish. And it's a wish without a budget attached. Every single requirement, functional or not, has to have some kind of business value, so we can figure out what it's worth and prioritize it against everything else we need to build. This leads us right into our next big topic, avoiding premature optimization. This is probably one of the most common traps in software development. This urge to optimize code for performance before you even know if there's a problem that needs fixing. The legendary computer scientist Donald Knuth absolutely nailed it with this famous quote. The point isn't that optimization is bad. Of course not. It's that premature optimization is bad. You should only spend your time and energy making things faster after you've measured and found a real, actual bottleneck that's hurting your system.
There's a great case study that perfectly illustrates this problem. On one project, a developer was dealing with an old legacy system and decided to build this incredibly complicated system just for handling error messages. Get this, a message would go into a commercial message queue, then into a list in memory, which was then checked by another list, and this weird pattern happened 7 times before the error message ever got to the user.
And here's the real kicker. This whole complex, convoluted piece of architecture was built to solve a performance bottleneck that didn't actually exist. The system never ever had the huge number of errors that would have made this design necessary. The lesson here is so simple, but so important. Don't guess, measure. So, if we're not supposed to guess, we have to measure. And that brings us to our third section, the art of measurement. To do this right, you need more than just a script that throws a bunch of traffic at your app. You need a proper, well-designed, and representative testing environment. This little story just highlights how critical the testing environment is. A team was being forced to do all their performance testing on this ancient, super underpowered hardware. The results were terrible, obviously. So they did some math and proved that their testing setup was actually less powerful than a handful of old iPods clustered together. It was a hilarious, but really effective way to show that for your results to mean anything, your test environment has to be valid. Now, in a perfect world, you test on an exact replica of your production environment. But for most big systems, that's just way too expensive. A much more common and more practical approach is to build what's called a slice of production. So maybe one web server, an app server or two, and a database server. But, and this is a really big but, you have to be super careful with this approach. It's so easy to fall into the trap of thinking that performance will scale perfectly. If one slice can handle 1,000 users, then 4 slices will handle 4,000. But complex systems almost never work that way. So taking results from a small environment and guessing what will happen on a big one, well, it's an educated guess at best, not an exact science. You have to be skeptical of those projections.
Okay, so the final piece of the puzzle is all about taking these ideas and baking them into your day-to-day workflow through automation. The goal is to make capacity testing just a normal, automated part of your deployment pipeline, not some big, scary manual thing you do at the end.
The huge win with automation here is getting feedback fast. When you build these tests right into your pipeline, you can fail fast. If a developer checks in some code that accidentally cuts your system's throughput in half, you can find that out within minutes, not weeks later. And that makes it so much easier to find the problem and fix it right away. A really cool strategy for automating this is called record and playback, and it actually uses your existing tests. The first thing you do is decide on your injection point. Basically, which layer of your app are you going to listen in on? You could do it at the user interface, or maybe at a public API, or even a service deeper in the system. So once you've picked your spot, you just run your normal acceptance tests like you always do. But now you have a recorder sitting at that injection point, quietly capturing a copy of all the inputs and outputs that flow through it. It doesn't change the test, it just listens in. What you get from this recording process is basically a reusable interaction template. So, for example, it might capture the exact series of requests that happen when a user places an order. Then you can go into that template and mark things like the customer ID or the order number as variables that you can swap out later. And this is where the magic really happens. You can take that one single template from one functional test and programmatically generate thousands of unique, realistic tests just by plugging in different data. You've just turned a simple functional test into a powerful capacity test that can simulate tons of users. So, to wrap things up, let's just hit the key takeaways here. First, treat your non-functional requirements like they're just as important as any other feature. Second, define what good enough means with actual numbers, not fuzzy statements. Third, don't guess where the problems are, measure. Avoid that premature optimization trap. And finally, automate your capacity testing and make it a part of your everyday pipeline. And that leaves us with this final thought. Making sure your code works, that it's functionally correct, is really just the starting point. The much bigger challenge, the real engineering challenge, is making sure that code can handle the pressure of the real world. The question isn't just, does it work, but will it survive?